This is my paper presented at CARME 2023. It's called Combining Categories for Each Variable in a Multivariate Categorical Dataset with Minimum Loss of Variable Association. The link here to multivariatestatistics.org contains some of my books available for free download. The YouTube channel Statistical Songs has many of my statistical songs. And on the CARME Network channel, there are many CARME activities and talks, including this one. As I often do, I start with a limerick summary of my talk, which actually says it all. I had this feeling one day, there are too many categories in my MCA. Choosing some to combine, so associations hardly decline, makes it much simpler, my biplot display. First, I start with some history on this topic. This talk picks up a theme from the 1980s, which caused a lot of controversy in the correspondence analysis world. In 1986, Doug Carroll, Paul Green, both of whom I knew very, very well, and co-author Catherine Schaffer published a paper about interpreting distances between categories in correspondence analysis. In the abstract, they say, a rationale is developed along with a scaling of coordinates that enables one to compare both between set and within set squared distances. I refer to these three authors as CGS. The following year they published a clarification, which was mainly about the scaling of the so-called French plot, which I've rather referred to as the symmetric map. I was referenced in these papers, but I had no knowledge at all of them. There was no Google Scholar notifications then, and not even Google, which recently celebrated 25 years of existence since its creation in 1998, which is not that long ago. But I happened to attend the second meeting of the IFCS, that's the International Federation of Classification Societies, in Charlottesville, Virginia in 1989, where Doug Carroll gave a presentation of this material. CGS used the column geometry of the indicator matrix in two-way correspondence analysis to conclude that all categories could be compared distance-wise, seeing they were columns of a single matrix. I was thinking to myself, there's something screwy here. So I asked the question, how could the distances between categories of the same variable, for example, be interesting, seeing they were dummy variables where there could be no overlap of the categories, because of the so-called disjunctive coding in the indicator matrix. In fact, Willem Heiser was in the same session, and he supported me in my doubt. They defended themselves, and after the conference, I read their papers. I was surprised they could even get them published. And then I produced a paper of my own criticizing their rationale, which was published in the same journal, the Journal of Marketing Research, or JMR, in 1989. My paper, The Carroll-Green-Schaffer Scaling in Correspondence Analysis, a Theoretical and Empirical Appraisal, said in the abstract, the author shows by a theoretical argument and by means of a simple practical example that the rationale on which the scaling is based is incorrect. Well, this certainly set the cat amongst the pigeons, and they were allowed to publish a rejoinder as a separate article in the very same issue of JMR, and right after my article, a practice I have never seen before except in discussion papers. They said, in their abstract, Greenacre's indictment of the scaling approach also implies an indictment of multiple correspondence analysis interpretation. This was not at all true. I had an interpretation of the relationship between rows and columns in correspondence analysis based on the biplot concept, that is, using scalar products and not on the interpoint distances of the categories as they proposed. I later extended this biplot interpretation to MCA. Now, without getting bogged down with this issue, I reproduce here from my 1989 paper the formula for the distances between categories as they occur in a two-way simple CA based on the indicator matrix. The contingency table is recoded in the equivalent form of the indicator matrix with two sets of columns, and then chi-square distances are computed between the columns of the indicator matrix. This produces two formulae, one for within variable categories and another for between variable categories. Neither formula is a justifiable between category distance. The within variable ones depend only on the inverses of the relative frequencies of each category. And the between variable ones involve the negative of the Pearson contingency ratio, which is the observed relative frequency divided by its expected value, which is promising, but they also involve the sum of the inverses of the relative frequencies, which makes it hard to justify it as a between category distance. Funnily enough, the year before, 1988, I published this paper in the Journal of Classification on separate clusterings of the rows and columns of a two-way contingency table, but didn't realize the connection with this between category distance stuff for CA and didn't reference it in my 1989 JMR paper. All that was about 34 years ago, and in a fairly short visit to Maurizio Vichi in Rome this year, last March, brought this whole topic back into prominence again. We discussed how to join together categories in an MCA, both within variable categories and between variable categories. Maurizio and I started working on this, and it splits nicely into two parts. The categories within variable problem, or the within set problem, for example, for simple CA combining rows with rows or columns with columns, which was the topic of my 1988 Journal of Classification article, but in that case only for two categorical variables. And the categories between variable problem, that is row to column, or in general, categories between any two distinct variables in MCA. Here I deal with the simpler of these two problems, just an extension of my 1988 paper to more than two variables. My 1988 paper proposed that the criterion for clustering two categories of the same variable would be in terms of the consequent reduction in the value of the chi-square statistic on the table, which is equivalent to the reduction in the inertia, since in CA inertia equals chi-square over the total of the table. This was equivalent to a weighted Ward clustering on the chi-square distances between the categories, where the weights were the usual correspondence analysis marginal relative frequencies assigned to the categories. So there was a clustering on the row categories and a clustering on the column categories. This weighted Ward clustering was already defined by Michel Jambu in Benzicre's lab in the 1970s when I studied there. The main contribution of my 1988 paper was to realize that a result by Hirotsu, published in 1983 in Biometrica on multiple comparisons on a contingency table, could be transferred to my pair of cluster analyses and give cut points on each dendrogram for significant clustering. This idea is easily extendable to more than two categorical variables in an MCA context by looking at the change in the total inertia of the MCA and identifying which two categories to merge, always within the same variable, that reduce the total inertia the least. What I consider to be the total inertia in MCA is the average of the inertias of all unique pairwise cross tables. That is the average of all the off-diagonal tables in the BERT matrix. Here we see the indicator matrix Z for a three-variable example, which leads to the BERT matrix and the computation of the total inertia of 0.531 as the average of the inertias of the three unique cross tables in this case. If you happen to have the total inertia of the whole BERT matrix, including the diagonals, this computation can be made by introducing a simple adjustment down of this total. Notice that simple two-way CA is a special case when there's just a single cross table. The algorithm starts with finding the closest pair, that is, that reduces the total inertia by the minimum. The number of possible category pairs to consider depends on the measurement scale, whether it is ordinal or nominal. For nominal categories, any pair of categories can be merged. But if the categories are ordinal, then it only makes sense to merge neighboring categories. For this example of 5 categories per variable, for nominal categories, there would be 10 possible category pairs to consider for each variable. If the categories are ordinal, only 4 category pairs, those that are adjacent, need to be considered for each variable. Once this minimum reduction is found and the two categories merged by simple summation of their columns in the indicator matrix, the BERT matrix is recomputed and has one less row and column, and then the next smallest inertia reduction is sought. The process continues until all the categories within all the variables have been merged and the inertia is reduced to 0. Here's an example taken from the ISSB survey on family and changing gender roles. I've used this dataset in several publications. It consists of 8 statements about whether women should work or not, with categorical responses on 5-point ordinal scales, from strongly agree to strongly disagree. Some of the statements are worded favorably towards women working. For example, the first statement, A, says a working mother can establish a warm relationship with her child, while other statements are negatively worded. For example, statement B, a preschool child suffers if his or her mother works. I use data just from the Spanish sample size of 2,421. And I first restrict attention to respondents who gave complete responses. And that's a sample of 2,107. That is with no missing data, and I will deal with missing data and the missing data responses later. The total inertia in this data set was 0.2215, and applying the algorithm that I just explained results in this agglomerative clustering of the categories. Interesting for me was the fact that the very first pair that is combined is H4 and H5. The disagree and strongly disagree responses to the statement, women should get paid maternity leave. In my previous analyses of these data, I had a problem with response category H5, which is given by only 2 Spanish respondents. So I combined it informally with H4. But here, this algorithm chooses it as the first pair to merge. Of course, it is because of the rarity of category H5 that it easily combines with the adjacent category, since changing the responses of only 2 respondents will have minimal effect on the variable association. Notice that the extreme categories, strongly agree and strongly disagree, are the last to merge, and the very last ones to merge are consistently those related to the strongest opinion in favor of women working. These are the biggest contrasts in the data and account for the highest inertia differences when these extreme categories are compared to the other categories. The dashed red line indicates the threshold for significant clustering based on Hirotsu's result. But that result was for 2 categorical variables, not 8. And the way this threshold should be modified is still to be investigated. But I used it anyway here as an illustration of what happens when the merging process is stopped at a certain level. Here we see an animation of this merging process. A total of 21 out of the 40 categories are merged. For example, H2, H3, H4 and H5 are all merged, and all that remains for this variable is the contrast between the strong agreement category H1 and the rest. Here we see the final result on the right. There's a reduction of 12.7% in the total inertia, but there are 33% less categories. The overall structure of respondents and response categories remains the same, but the display is less cluttered and the interpretation is simplified. On the right are all the extreme responses, stretching from strong traditional views about women working at the bottom to strong liberal ones at the top. On the left are the moderate responses, here zoomed out a bit, with a similar traditional to liberal gradient from bottom to top. The clustering of the categories within each variable arrives at the top where all categories have been merged and all the inertia has been lost. But the clustering can be continued now at the level of the variable, again starting with the total inertia of the 8 variables and merging the variables, which again leads to inertia loss at each step. Merging the variables is based on association. High association, that's high inertia, means they are close. So B and C are the first pair of questions to be grouped, since the inertia of B cross-tabulated with C is the highest. These two questions are quite similar in that they are both worded negatively towards women working, and both concern suffering of children and family if the mother works. The inertias of the other variables are updated by averaging their inertias with B and C. The inertia loss in the reduced table is computed to determine the height of the merging of the two variables, and then the process is repeated. The final variable to merge is H, which has the lowest association with all the variables, since it is on a less related topic about women getting paid maternity leave. What is nice in this double clustering, first of the categories within each variable and then the clustering of the variables themselves, both on the same scale of inertia, from the total inertia reducing to 0 in each case. Now, what about the more than 300 respondents that had some missing values in their responses? In MCA, these are just an additional sixth category for each variable. If these are included in the merging exercise, they clearly do not fit with the ordinal nature of the others. These missing value categories can be allowed to merge with any of the other 5, whereas the other categories still have the ordinal constraint. Here is the clustering of categories and variables with the missing response categories in red. It turns out that in 5 out of the 8 variables, the missing value categories cluster with the already clustered categories of agree, neither nor, and disagree. Variable G, the most anti-feminist statement, a man's job is to work, a woman's job is the household, is a particular exception, where the missing value category joins the strongly agree response. To try to understand why this occurs, the variable G is cross-tabulated with age, education, marital status, and gender, and visualized using correspondence analysis. Although the category merging does not take into account the demographics, the missing value category is indeed associated with the strongly agree and agree end of the scale, corresponding to highest age group or lowest education group or widowed respondents, which are the most traditional conservative demographic groups. So in summary, there seems to be some redundancy in the categories that can lead to simplification of the response coding, by merging categories that lead to very little loss of association between the categorical variables. The fewer categories there are, the less cluttered are the MCA maps and the simpler the interpretation. Which categories that can be merged depends on whether they are on nominal or ordinal scales. The results can be shown in a stacked double dendrogram where first the category mergings are shown and then the variables themselves are clustered. Both dendrograms have the same scale in terms of loss of inertia at each cluster node. The issue of statistical significance remains to be investigated, which will round off this work quite nicely. What I have shown applies to merging categories within each categorical variable, the within set categories. And in further joint work with Maurizio Vichi, the objective is to merge categories from different variables. In this way, we are finally resolving the dilemma raised in the papers in the Journal of Marketing Research at the end of the 1980s. Thank you very much.